Okay. So the assignment today is going to be a summary of some things we've done, but yet we're also kind of going to go old school and tie in some old ideas about angular motion. So let's say that I happen to have a spring. You all have done this, right? And you're going to hang a mass from it. Follow Hooke's law. If you do a graph, you put force on the x-axis, or force on the y-axis, x on the x-axis. You can graph it old school. This should not be new to anyone. This should be, oh, we got this. This is also a linear function. Do you have to worry about the y-intercept? No, because if you don't have any force, you don't have any elongation. So this is just a linear function. Now, because of the fact that you're letting gravity do the work, how are you going to calculate the force part of that? Do not make this difference. Whatever the mass is times g, right? Okay? And that would equal k times x, right? So once you get at this, you could also realize, because that's going to be elongation, that would be k times delta L. So if you get a situation where you say, okay, once you get it like this, there's a whole bunch of different things you can do with it. So you could find the value of k, which would be just be what? Yeah, the spring constant. It would be the slope of the line. If you knew what the spring constant was, and you knew how far it stretched, and you know what the mass is, you could actually use this to solve for g. So let's say, again, you're starting over. We've lost all knowledge. We don't know what the value of little g is. Hey, set up a spring. If you know what the mass is, if you know what the spring constant is, you know how far it stretches, you can use that to find the gravitational acceleration. Okay. Now, we got to go old school. Old school. Not real old school. Some old school. So, when you talk about angular motion, you have theta, omega, alpha. Anybody remember what theta is measured in? Radians. Okay? Omega is in radians per second, and this is radians per second squared. Now, here's the leap of faith that you need to take in terms of how circular motion can be modeled with angular motion. Okay? So here's, you have to use a little bit of imagination, but not a whole lot. So imagine that you have a spring, and you're going to make something oscillate back and forth like this. Okay? So you would have this spring, and you would see that mass oscillating back and forth like this. Now, imagine that you have the green spinny thing, okay? And you have that mass going around in a circle. So if you could not judge depth, okay? If you could only judge this motion. So what you would see is that you would see this mass going back and forth, okay? So this mass going back and forth on this spinning tray, you could not tell the difference if this thing is oscillating back and forth. That's assuming that you could not judge depth. So if this thing was oscillating back and forth like this, or if it was going around in a circle, you couldn't tell the difference between those two motions. Because all you would see is it's going back and forth. So you can model the oscillation of a spring going horizontally in terms of angular motion. So we're doing a little bit of voodoo. Okay? Not bad, just a little bit. So if you look on your textbooks, on page, I don't know why I lost my grid. You have this. some ideas together. So omega can equal 2 pi f. Okay, now let's see why this works. So what are the units, and I'm going to morph these two equations together in just a second. So omega is in what? Radians per second. So this is technically 2 pi radians, but we really don't call it radians, okay, but it's just 2 pi radians because it's a dimensionless number. So technically, kind of in dashed letters, I'm going to put radians, okay? But frequency is 1/2, okay? So if you have 2 pi f, that can be modeled as saying that has the same units as omega. So something oscillating with a certain frequency, you can also express it in terms of omega. So you've got this equation here. So all I did was say, all right, frequency and period are inverses of each other. So all I did was that I substituted 1/f in there for t. That's all I did. It's a simple substitution. Nothing wonky. I just did a simple substitution. So then when I look at this, I get a cosine 2 pi f t. Okay? So all I did was flip up the frequency and put that up there. So right here, you'll notice that I've got this 2 pi f thing right there. So what is 2 pi f also equivalent to? Omega. So I can also write this as a cosine omega times period. So this is where these two things intersect. So if I know this thing is moving around in a circle at say 5 radians per second, whatever that value is, so I look at this and I time it. Oh, hey, it's moving at 5 radians per second. So that moving in a circle at 5 radians per second would be the exact same observation as if I had that spring going back and forth like this. So this is where these two ideas cross over. And it's the same thing in terms of units. So if I start with 2 pi t over t, what units do I get underneath inside that bracket when I take 2 pi t over t? Not make this difficult. Just the units. Well, what's little t going to be measured in? Seconds. What's big T going to be measured in? Seconds. You have no units inside of that. Okay? There are no units inside of that. Now, look at this. What is omega measured in? Radians per second. And I'm multiplying that by time, which is in seconds. You only get radians. So in both situations, this is why you have to be in radian mode if you're doing these function equations, because of the fact that you get radians inside that function. Okay? So depending upon what you're given in the problem, you could either set it as there's 3 options, and they all mean the same thing. You could have little t over big T. You could have 2 pi f t. Or you could have omega t, depending upon what you're given in the problem. Okay? Because they're all equivalent. It's just, are you talking about a circle, or are you talking about an oscillating spring? Just depends on what you're given. Okay. Now, here's the mix system. So we said when you have an oscillating spring, what are the 2 maximum things that you could have? You could have it as all U, or you could have it all as kinetic. Now, we're going to get a little important in terms of variables. So if it's all U, that's going to be 1/2, but instead of x, what are we going to use? Amplitude squared. And that kinetic would be 1/2 m V max squared. Okay? Now, what I want to do, because this is going to be important in terms of how you can use this equation, I want to solve this thing for V max. Okay, so I want to get V max by itself. So conveniently, what's going to happen to the 1/2? 1/2 are going to cancel out. So I do a little bit of voodoo. I take the K and divide it by the M. And then I've got A squared. And then I'll take the square root of that to get V max. But we can simplify this a little bit more. Because what's the square root of A squared? So V max is going to equal A times the square root of K over M. So now, again, play with this in terms of variables. If you want a big V max, do you want a big amplitude or a smaller amplitude? Big. I want a bigger amplitude, okay? Because the bigger the amplitude is, the faster it's going to be going in the middle because I've stored more kinetic and potential energy. If I want a big V max and amplitude is the same, do you want a stiffer spring with a big K or a smaller K?
Big K.
You want a big K, right? Because again, you're storing a lot of energy, that's going to produce a big V max. If you want a big V max, what do you want to have happen to your max? Small, okay? So if I look at this, okay, hey, that's going like this. But if I put that second mass on the end of this, notice that goes much slower. So I have the same value of K, I have the same amplitude, but if I make that mass bigger, my value of V max becomes smaller. Okay, now one last voodoo, and then we're done. Okay? So this is this equation that we derived earlier. So this gives you the frequency of an oscillating mass, K over M. But we're going to do a little bit of voodoo. I'm going to multiply this by 2 pi. So I have F times 2 pi equals the square root of K over M. But what does frequency times 2 pi equal?
Omega. Beautiful.
Over M. Now, let's say you wanted to solve this for K. Let's say you want to find the value of K. How would you get that by itself? So you'd have what squared times mass equals K. So that's another way that you can find the spring constant. Okay? So if you know how fast something, that radians per second, and you know what that mass is, there you go. Now, interesting thing. If you double the value of omega, what would happen to the value of K? It would go up by a factor of 4. Last voodoo. V max can equal 2 pi FA. Well, what does 2 pi F equal?
Omega.
So you can also write this as or a button, depending upon how you want to arrange that. Okay? All right. So
this is thing you did earlier.
yes.
Oh.
I just saw what he started with. I was like, oh, that's it. That's it. Especially after what he just did. This reminds me of what class did this happen in? Was it geometry?
Yeah, where
Mrs. Morales like wrote like a thing. Yeah. Wait, somebody did this. Yeah.
Yo, I don't think Chloe gets to do it.
What's the difference between questions and
He
problems?
just has a voice. You have to fully play it.
Maybe explaining and then.
No, that's not what
Now, this looks much more daunting than it is. A lot of these are multiple choice questions, and it looks daunting, but it's not all that bad. Because a lot of these are literally just multiple choice questions. So, when you get to question number 3, for those of you that are new to this textbook, at the end of the chapter, there's a section called questions, and there's a section called problems. Okay? So these come out, that's why I said, here's the questions, here's the problems. Now, same rules apply, answers on the left, work on the right. Okay? So this is just nothing but the equations that we've been working through. Okay? It's just an application. So the test overall, this is going to be on Wednesday. So here's the story. So next week on Monday, we'll finish up basically all there is to learn in chapter 14. We'll review on Tuesday. Test is going to be on Wednesday. Okay? So that's how that's going to play out. All right? So, good luck. What? Go.
Yeah, my backpack.
What is right? Like, what is this?
What's right?
It'll make sense because this book defines anything moving right as positive, anything moving left as negative. That will make sense when you get to the right.
No, there's different stuff in the textbook.
Huh?
They're outside the
What?
This was the order, right?
That, right, in this book, they define anything moving to the right as being a positive value. Okay? Anything that's moving to the left is defined as a negative value. That's all that means. It'll make sense once you read that problem. What? I will give you any of the weird equations. If it's not on the sheet, I will give it to you.
Just know to put like maybe if I add. I feel like you do that.
We have like 22 minutes.
Maybe you must have the technique.
I'm showing you.
Like 20 minutes.
Yeah,
Wait.
We can all just sit here.
What question are you on?
Just the last 2.
You need to finish your last.
Yeah. Awesome. I can just do my calc. I'm in calc 1 like a week.
What is that thing called? Rolling disc. What do you call that thing? The carousel?
Hey, Gavin.
Carousel or
What?
the spinning table?
Well, today's the day I break my back. Officially. You've already been carrying them, haven't you? I've carried my other textbook for English is heavier, so I'm not like so dying, I guess. You're in shape for it. Yeah, I'm used to it. So you have A push, this one, and then your calc too? All 3 in your backpack?
Oh
no, I don't carry all 3.
Okay.
I only carry physics. Okay. That's good. I was gonna say.
I was like, calc, you don't even really need the textbook, but I still checked it out.
Mm-hmm.
And then, A push, he tells you if you need it, and you only need it like sometimes.
You're a hater.
Yeah, I am.
This is not part of the answer. At what times? Like 17, like 17.
I haven't done it. I'm doing it right now.
Oh.
I just looked at
I'm
it.
talking.
How do I?
I already
You got food?
No, it's when you do the two
I'm hungry.
fields.
No, I just looked at it.
Pop-Tart?
Give me 3 seconds. I got it.
Yeah, one day that's the worst one to eat.
I thought you were
I am sure it's
like,
Wait, how am I supposed to find it?
Nathan.
Hey, I'm just saying, Brian.
You
You
better pay.
I can do that on.
Oh,
I can
yeah,
do
that
that.
sounds
Oh, I'll take it. Thank you. I can see, I need raises.
I know you have money on it.
I think I covered my butt.
No, not on this one.
Do you know how
Well, I need a paper.
What, in like stacks of $1 bills?
Yeah, well,
The bride.
Oh wait, that's Sydney, what's SMH?
I haven't read the question yet.
Read it!
I just lost my eraser.
Okay, so you can. Oh, so now we're just taking it up. That's how you do
Oh,
it.
seconds.
We do calc. So at least I could get that. Got a lot of homework to do.
Mm-hmm. Sure do.
And then you put your.
Guess what I'm doing this weekend?
All his homework.
Mm-hmm. All for him.
There's this like
If I got $1 for every hour I spent,
Yeah, you know me with my calc.
Where's this?
it's still on.